In the first part of the section, we studied double integrals in polar rectangles. This second part will deal with general polar regions. Let's see the theorem. F is continuous on a polar region of the form. Now D, for this region, angle theta is from alpha to beta. And for each theta, each angle, now R is from H1 to H2. Look at the figure left-hand side. Angle is from alpha to beta. Now for each angle, theta, now R is from here, bottom R to top R, H1 and H2. So we are trying to access the region radially along this way. Okay. So for the integral, double integral, we can get it along with this iterated integral. Now theta, out integral, moving from alpha to beta, and for each theta, now R is from H1 to H2. That is the integrand expressed as a function of r and theta. And dA is changed to be r dr d theta. Okay. In this problem, we'll try to plot the four leaved rows r equals cosine 2 theta. This the maroon color curve is the four leaved rows. In this problem, we'll see how to plot the curve. For such polar curves, you may start with theta r coordinates, and then you can convert it to the xy coordinates. Okay, let's the coordinates, and that is r direction, that is a theta direction. Okay, that is a theta, and that is r direction. Okay, now once the theta is 0, then start with 1, r is 1, and go down and up. This one cycle, and now go down and up again. Okay, so here this position is 2 pi, and that one, the center, that is pi. Okay, and of course this is there's half pi, and that is a pi over 4, and so on. Once the theta is pi over 4, then 2 theta will be pi over 2. So cosine pi over 2 must be 0. And now r becomes negative. Okay. For that, so that is in theta r coordinates the curve. Okay. Now we have to convert it to the xy coordinates. So in order to do that, let's try to name the parts. Okay, this portion is 1, that is the second portion, third portion, fourth portion, and that is the fifth one, and that is now, okay, that is the sixth one, that is the seventh one, that's eighth one. Okay, now for each part, we'll try to convert to the xy coordinates. Okay. Now, okay, here the r is moving from -1 to 1. So we start with a circle of radius 1, like that, in xy coordinates. Okay, that is coordinates. And then Now, angle is from 0 to pi over 4. That means the angle must be, okay, let's try to make a 45-degree line like that. And later on, we'll use this portion. Okay. So for this first part, angle is from 0 to pi over 4. So this is the region for part 1. So angle is moving from 0 to pi over 4, but now R is becoming 0 from 1 to 0, right? So angle is increasing, and then gradually R becomes 0. Okay, so that means that start from here R, but angle is increasing, but R is becoming smaller, so that it becomes 0. So that is the corresponding part of this, the first part. Now, how about the second one? This one, now angle is from pi over 4 to pi over 2. For this one, now in xy coordinates, this portion. Now, okay, R is negative. So rather than this one, let's try to is absolute value. So that in positive 1, we consider this one first. For this one, now angle is from here to there. The radius is from 0 to 1. So that one, for this one, we can make here, that is now, angle is increasing, now becomes 1. R becomes 1 as angle increases like that. So that is the corresponding part of this one. But the original one is a negation. That means we have to deflect this one and rotate by pi, so that this one must be rotated here like that. So that is now the part 2, right? How about part 3? Again, same. Yeah, that is from here to there is related to this angle. For that one, now if we consider the reflection, then radius is from 1 to 0, reduced like that. It's reduced like that. Now, its negation must be rotated, which is that portion. That is now part 3, right? Similarly, you continue, and this one is from here to there. Now angle is increasing from this to here. Now R is increasing from 0 to 1, so that you can get this one. That is the fourth part. And if you do the same, then fifth part will be that one. And the sixth part will be this one. And that is the seventh part. If you continue this one, then eventually there is eighth part. Okay, in this way, you can get the 4 Lewis rules. And for other polar curves, you can do it. First, try to draw a plot in the theta r coordinates, and then you can convert it to the xy coordinates. Okay. Now, for the 4 Lewis rules, r is cosine 2 theta. Now, we try to find the area enclosed by one loop. So, for example, in this figure, let's try to find this one. And now angle is from, if we consider that one as minus pi over 4, then it's okay. Minus pi over 4 to pi over 4, and that's angle. This is a polar region. And R is from here to, you can access this region radially from here to that one. But at this point, for each angle, that one will be now R equal cosine 2 theta, right? So its beginning is 0, and that is end point of R for given angle, right? Okay. So the area can be found in this way. Double integral over the dA, this angle is from minus pi over 4 to pi over 4. And now for each angle, R is from 0 to cosine 2 theta. And dA is changed with R, dr, d theta. Okay. Now, the remainder part is just a simple calculation. Okay, that is same as integral minus pi over 4 to pi over 4. That one, antiderivative is half R squared, and R is moving from 0 to cosine 2 theta and d theta. Right? Okay. Now for that one, now half can go out, and then minus pi over 4, and once R is 0, then we can ignore this evaluation. For that one, this is now cosine squared 2 theta, right? D theta. Now to get the integral, we may try to use the formula. Earlier, we considered this one, for example, cosine squared x equal now half of 1 plus cosine 2 theta over 2, and sine squared x, okay, that is 2x, not theta, and cosine squared x is now 1 minus cosine 2x over 2. We consider this formula and we'll use that. Okay. So from here, that is half minus pi over 4 to pi over 4. And that is half. Now x is 2 theta. So that will be 1 plus, and cosine 2x, that means that is 4 theta. And t theta. Okay. Now theta is moving from minus pi over 4 to pi over 4. Then 4 theta will be from minus pi to pi. That means this portion will make whole cycle. For cosine curve, once you consider whole cycle, then halfly positive and halfly negative, so that you may ignore this portion. The contribution to the integral will be 0. Okay. So remainder part is half. So that along with this half, 1/4, and that one, the length is pi over 2. So we can get pi over 8. That's the final answer. Okay. Find the volume of the solid that lies under the paraboloid z equal x squared plus y squared above the xy plane, and inside the cylinder x squared y squared equals 2x. Now we summarize how to solve the problem here. You have to first find what the polar region looks like. And for this problem, now translate this equation into polar coordinate and try to recognize the region. You may change this one into this form, then that is a circle of radius 1 centered at 1 and 0. Okay. Now, here for the integrand, and you have to change this one in polar coordinate. And now dA will be changed to be r dr d theta. Okay, everything else is okay except that one. Now for this one, x squared plus y squared equal 2x. And the region is inside this cylinder. Okay. And x squared plus y squared is r squared in polar coordinate, and x is always r cosine theta. We may eliminate one r both sides, so that there will be r equal 2 cosine theta. That is the polar curve. Okay, this one is the same as that, so that if you try to draw this one, then there will be a circle of radius 1, and that will be, this is x-axis, y-axis, and x-axis. The center is 1, and of course there's 2, and this is the region. And that in xy plane, now above this xy plane and below of that, so that okay, once it is a D, then volume must be double integral over D, and here x squared plus y squared dA. Okay, now this is polar region. Angle theta is minus pi over 2 to pi over 2, and r for each theta, okay, start from 0, and we can access this region radially from 0 to this point, but this point is the same as that one, right? So that is from 0 to 2 cosine theta. Okay, so for this integral, we can convert this one into the polar coordinates. Okay, angle is minus pi over 2 to pi over 2. And r is from 0 to, now that is 2 cosine theta. And the integrand x squared plus y squared in polar coordinates, there must be r squared, and dA must be here r dr d theta. Okay, that's the formulation, and we have to now calculate. Okay, for this one, okay, our integral we keep the same, and this is r cubed. So that is 1, okay, r cubed is antiderivative is 1 over 4 r to the 4, and from 0 to cosine 2 cosine theta, and now d theta. Okay, for this portion, and 2 to the 4 is 16, so along with that we have 4. So we have here now 4, okay, integral minus pi over 2 to pi over 2, 4 cosine 4th power theta d theta. Okay, we have to evaluate this one. Now how? Okay, now here for cosine fourth power of theta, that one can be written in this way. Cosine for theta, that is cosine squared theta whole thing squared. But that one, by using the formula, we may write in this way. That is 1 plus cosine 2 theta over 2 and squared. Okay. So we have here 1/4 and the square is 1 plus 2 cosine 2 theta and plus cosine squared 2 theta. Right? Okay. Now, for this term, cosine squared 2 theta, we can change this one again. That is 1/4, 1 plus 2 cosine 2 theta, and plus that one is, okay, we'll try to write down this one separately. 1 is 1/2, and plus 1/2 of now cosine 4 theta. Right? Okay. That's here, this term, same as that. Now, for each one, we can get integration. Now, theta is moving from minus pi over 2 to pi over 2. Then 2 theta is minus pi to pi. So that will make no contribution. The value must be 0 after integration. And also for this one, the same. You can ignore that. And so that from here, the constant part will be 3 over 2. Okay, addition is 3 over 2 and 1/4. So that 3 over 8. So rather than that one, we consider 3 over 8. So this whole thing can be replaced by, okay, so it's a 3 over 2. Okay, now the interval length is pi, and the constant 3 over 2 times pi. That's the final answer. It's not so much complicated, right? Okay. Evaluate the double integral. Okay, this problem is a variant of one earlier problem. Now we want to get the double integral. Now first y direction integration and outer x integration. If we try to do it in xy coordinate, then it's very hard. It's not easy, possibly impossible. Okay, so that we have no elementary anti-derivative for this term, so we cannot get it. And to get the integral by converting to polar coordinates, first we have to recognize the domain. From lower and upper bounds, we can see that x is moving from 0 to 2. Okay, let's try to use this one. Okay. Now, x is moving from 0 to 2. So it's 2. Okay. There's x direction. And that means, okay, this portion is that y is moving from 0 to 2 and square root of 2x minus x squared. This is a bottom y, there's top y. Okay, we focus on top y, bottom y is 0. Top y, then y equals, now square root of 2x minus x squared. Square both sides, then y squared, move this one to the other side, then x squared plus y squared equal 2x. Okay, the reason we say And this problem is a variant of problem as here. That one is exactly this one. But we know that this one, of course, for this one now, y must be non-negative, so that we have only half of that upper portion. Okay, so this y is moving from 0 to top y, so that is, this integral is accessing the region vertically in this way. For each x is accessing vertically. Anyway, this is the region D. This is a polar region. Of course, that one is r equal to cosine theta. We know already from the previous problem. Okay, so the given integral is the same as, now angle is from 0 to pi over 2. And the earlier problem is now, because of that portion, minus pi over 2 to pi over 2. But for that one, y is non-negative, so that from 0 to pi over 2 angle. And for each angle, r, bottom r is 0, top r is 2 cosine theta. And that one, the integrand is now r, and there's dA must be now r dr d theta. Okay, so that is now from 0 to pi over 2. And there's r squared, so 1/3 of r cubed from 0 to 2 cosine theta. After evaluation of this one, we have to make theta integration. Okay, that one from 0 to 2 pi, and r is 2 cosine theta, it'll make 8, so the 8 over 3, and cosine cubed theta, the theta. Oops, okay, that one is not 2 pi, this must be here pi over 2. Okay. Okay. Now, how can we get the integral? That is, so we'll consider that cosine cubed theta. Now, cosine cubed theta, it is a typical technique. Okay, that is cosine theta times cosine squared theta. Now that one is cosine theta times cosine squared theta is the same as 1 minus sine squared theta. Now we can expand, that is cosine theta, and minus cosine theta sine squared theta, right? Now, for each one, you can get antiderivative. Okay, from here, if you try to get antiderivative for this one, you can get here down sine theta. From this one, okay, the main part must be sine cubed theta. Okay, sine cubed theta. If you make a derivative for that one, then that will make 3 times sine squared theta and cosine theta. The 3 will appear extra, so we have to put here 1/3 and this negation. Okay, that's antiderivative. So that one will be now 8 over 3, constant can go out, and that is antiderivative with sine theta minus 1/3 of sine cubed theta. Theta is moving from 0 to pi over 2. Once theta is 0, that's 0, but pi over 2, then that will be 1, but that will be now sine cubed theta, again 1. So we have here now 8 over 3 times 1 minus 1/3. So that's 2 over 3, right? So that is 16 over 9. That's the final answer, okay? That's the end of section. And we have one more page here. I'll try to record it separately for the volume of M-ball. Thank you.